Hello, everybody. Welcome to the July, almost August Gazebo community meeting. We have the agenda that I'm going to start sharing right now in a second, as usual. And the plan is very similar to the usual plan. So we'll start with the announcements. We'll go over the usual Gazebo news over the last month, and then we have two guests, Shashank Rao and Arjo Chakravarti, and they will go over some interesting project for Gazebo, so for doing ray tracing using some dependencies specialized in doing this type of things, and they'll go over the details. And then, as usual, we have plenty of time for questions. I'm not sure how long it's going to be Arjo and Shashank's talk, but typically we have plenty of time. So you have any question related with the talk, please let them know. Or if there's anything related with Gazebo, of course, let us know. We'll try to do our best to reply. I'll start with the news this time. Probably next time that we do this, Adisu will return to be the person who goes with the news as usual. And the idea here is to go over the roadmap updates that we promised to do for the Jerry release, because right now pretty much all the Gazebo team is focused on the Jerry release. We are on we just passed the feature freeze date just a few days ago, and we are in this summer time where we're now gonna be testing the current version that we have, that we're gonna release. We'll do the usual bug fixes. We'll do the testing parties and tutorial parties, and then finally we'll release this. So this is pretty much like an update of the roadmap that we promised for Qt. So we said that we were going to migrate Qt, the code from Qt5 to Qt6. This is mostly done already, but something that's new is that there's a Qt6 migration tutorial. It's available in this link. Also, we're gonna provide an additional underlying middleware option for GC transport based on Zeno, and this is gonna be, I guess, the first release that's gonna have that option starting in GC transport. Obviously, we'll have some limitations, but we think most of the functionality is going to be there by the time of the Jerry release. So we merge a few interesting PRs, part number 7 and part number 8, to fix some PubSub issues and some service issues that let us enable also most of the tests that we have for PubSub and also for services to confirm that things are working. So right now, we have ZeroMQ running like all the test suite, or almost all the test suite, and then we are trying to achieve testing parity with the Zeno-based approach, just to give us confidence. We still have iterating on part number 9, which will support some specific use case for services that are not working right now. Also, command line binaries was something that we promised, and it's going to be released for Jerry, and we're going to be using mostly C++ binaries for the command line tools that we use, as opposed to the usual Ruby-based commands. And most of them are good to go. GSystem was also heavily under development for this particular feature, and the server part, the server executable, was also merged. We're actually dealing with some issue. It's related with Qt on Conda on Windows, so that's going to affect that. We're not sure we'll be able to fix it on time, but we'll try our best. In Bazel, it's also an item in the roadmap. Same thing, we pretty much finished the migration from most of our libraries to the Basel central repository. So we have the GSoC rendering sensor sim already available over there. The main limitation that we have here is that there's not going to be a GUI for now. We needed to take some compromises, but it's going to be over there, at least for the server side. That was something also on the roadmap, download fuel models on the background. We also decided to take some compromise here, and then what we're doing right now is that leverage multiple threads on your system and try to download like all the 3D assets in parallel as much as possible before Gazebo starts. So we think that will accelerate the time or reduce the time that before you can actually use Gazebo while downloading models without, I guess, compromising a lot of the code for the release right now. So we decided to use a simpler approach for this, but I think it's working. Some of these slides are a little bit out of date. So in this case, the remove version number from the package names is something that we've been doing, and the we just needed to complete the, I guess, like the aliases for the packages that include names on it. So for example, the Jerry packages, similar to what happens in the ROS ecosystem, where you have like ROS dash name of the ROS distribution and then the name of the packages. So we're going to do something similar. That part was still pending, but all the PRs have been already now filed. So we're very close to have this functionality available. Another item that we decided to squeeze also for the Jerry release is to implement the standard simulation interface. This is like a joint effort across many different, well, not many different, but some different simulators, including like O3D, the Nvidia folks, for having like a standardized way to control certain aspects of the simulation via ROS. So there's like a well-known API, a well-known interface based on ROS, and then all the simulations, or we are trying that all the simulations follow that API and implement what's described in that specification. And this is what we did. We are trying to have a first pass of that, and we are integrating some of that in via ROS-GC. So there are some PRs here, but not of them. So you can see, for example, here on the ROS-GC repo, this active PR that Adisu created, where there's a lot of movement right now for doing this. What else? Yeah, other updates. So in the infrastructure side, there were a few updates. One is the auto-release Gazebo libraries project. This is an effort. Don't quite remember if I mentioned this before, but we are trying to reduce the friction, trying to reduce the time needed to make a Gazebo release, and maybe reach a point where we can do this pseudo automatically every certain time. We're taking baby steps into that direction, and then some of these steps were implemented, and then we have like a pilot program starting in GC Transport. This is gonna be, maybe we'll like seriously, we'll probably start playing with this after the release. But the idea is that every PR now is gonna include a change log. There's gonna be a way to mark that this patch it's representing like a bump in the minor release or bump in the patch version of the release, etc. And then our tooling will be able to handle those things in a more transparent way, in a more automatic way. So I'm sure we'll go back to this at some point after Jenkins. Also, the infra team was very busy dealing with a big update. So our Gazebo Jenkins build form was upgraded. It's now using modern Jenkins versions, and also based on a modern Ubuntu version. I believe it's 24.4, because we were using an older one. Yeah, big change. I think most of the behavior is working as expected. We might have some hiccups here and there, but yeah, kudos to the infra team. And I think that's it, unless Adisu corrects me and want to add something.
Did you mention feature freeze?
I think so. We are already in feature freeze, so then our next stop will be on the 25th or something like this, or August.
Yeah, and we can maybe start talking about the tutorial party,
Mm-hmm.
which will be in, let's see, what is it? When is it exactly?
So,
It will start in August, on August 27th. We'll have a community meeting just like this to go over what the tutorial party is, and then we'll kick it off. So, yeah, mark your calendars for that.
exactly. That next community meeting will be a little bit special because we won't have the usual guest. This is we'll be using it for triggering the party. Question, Jacine, go ahead. You have a question?
Hello, everyone. Can you hear me?
There's some echo, but I think
Okay.
okay.
For the Gazebo server, I think it's slide 5. I'm trying to.
I didn't catch what you said, Jacine. You're breaking up a little bit. Could you perhaps type it on the chat? Your sound is not good. Do you mind to type your question in the chat?
Okay, for the Gazebo server, I think slide 5. Is it running on the browser if I make it a container with Docker Compose or require some additional?
I'm not sure if I catch the question. Did you say if it's possible to use Docker Compose to launch Gazebo? Was that along those lines?
Yes, exactly. I think that, I guess slide 5 talked about the graphic unit interface about the server. Like in the classic one, there is the GZ web, which can make the Gazebo run on the browser.
You have to be in a very busy town. Um, I don't quite understand the whole question. There's a lot of noise. I think you were talking about the server. If we, I suspect, are you asking if we can? That there's some difference between classic and Gazebo, and did somebody understand the question? There was a lot of sound. Sorry, a lot of noise.
I think he's talking about something on slide 5.
I don't know. Perhaps if you could write it on the chat, it'll be easier, Justin, and then we can go back to that and answer that question if you don't mind. Yeah, no problem. But I couldn't hear it very good. I'm talking about the GUI when we run Gazebo on the browser. Okay, so this is like GC Web question. I think it's slide 5 or 6. Can you share link? Okay. So, I'm not sure that I don't think there's anything here related with GCWeb on these slides, as far as I can see. Launcher GUI. This is Bazel stuff. Yeah, there's nothing here that talks about GCWeb. This is like migration from Qt5 to Qt6. This is an issue that we found on Conda while we were working on the standalone executables. I mentioned that for Bazel, so the versions that we have right now are not going to have GUI. And I think that's it. I'm happy to follow up with you perhaps later, if you don't mind, to contact me and we can clarify this. I see that Adiso is answering some, sending some links here. Okay, cool. All right, any other question before we jump into the talk? Anything about the Gazebo news, etc.? All right, so let me go back to the agenda and then let's jump into the next topic. So it's my pleasure to introduce Shashank Rao from the Indian Institutes of Information and Technology in Nagpur and Arjo Chakravarti from Intrinsic Innovation in the office in Singapore. And they're going to be talking about vendor-agnostic ray tracing sensor plugin for Gazebo. Very hot topic these days. So whenever you're ready, Shashank or Arjo, you are up.
Hello everyone. Am I audible?
Mm-hmm.
Yeah, so I'll just share my screen to present.
Sounds good. We can see it.
Yeah, so if everyone can see my screen and can hear me, so that's good. So
Good.
hello, good. So it's currently night time. So good evening, everyone. Let's start. So here's a presentation about the project I've been working on along with Arjo. So it's a vendor-agnostic ray tracing plugin for Gazebo. So firstly, a bit about me. I'm a GSoC contributor at Open Robotics. So I started working around May and the actual coding began around June. So it's almost the midterm of my, so we're almost midway through my GSoC term. And my mentor is here, Arju Chakravarti from Intrinsic. So firstly, let's talk about how are LiDARs rendered currently in the Gazebo world. So for the current approach is rasterization. So what is rasterization is it's basically, if we talk about simple analogy, it would be like taking a 2D photograph of a 3D scene. So as you could see here, triangle. So the 3D world is divided into triangles to project them onto pixels. So then we estimate how many pixels are exactly overlapped by the triangle. And then we draw a rough image around pixels of that supposed triangle. So take multiple triangles and you get the complete scene that you're trying to render. So this is the rasterization. So this converts a 3D scene constructed up of multiple triangles to and polygons into a 2D image. So this could be used to estimate like color of each pixel in a 3D world and even depth to some extent. So how is it useful for LiDAR simulations? And how is it used? So first, depth image 2D depth image is rendered. As I said earlier, a triangle that is if a pixel is overlapping a triangle, so for every pixel that is overlapping a particular triangle, a depth value is created for that particular pixel, and in that way, a depth image is created. So a 2D after a 2D depth image is created, it is projected back into 3D. So like for every pixel, we have a uh, value for the depth. So this can be calculated using the camera's mathematics. So and this distance that we just calculated using rasterization, we can estimate the XYZ coordinates for that pixel. So like the exact coordinates for where the pixel actually intersects with the triangle, the object. So in a simple way, we could say that the workflow goes like there's the 3D scene, then we create a 2D depth image out of it using rasterization, and using some clever processing, we convert it back into a point cloud. But it sounds easy, and it actually is, because all the GPUs are very good at rasterization. But the real drawbacks of this approach come when we talk about LiDARs, because LiDARs are not just 2D, they require a particular field of view, and that's typically 360-degree. So for 360-degree LiDAR, a single depth camera cannot work. So we try to implement a multi-camera solution. So for this, 6 depth cameras are taken. But if we render 6 depth cameras simultaneously, this would be very expensive on our GPU performance. So that is why we have to downsample everything, and then after we get a 2D depth image out of every camera, we try to upsample everything again and then stitch everything together to actually make a 3D point cloud out of it. So because of all this processing, the actual whole process becomes very complicated, and it takes like performance heavy as well. So hence the actual workflow would be like a 3D scene, then we take multiple depth cameras, say 6 cameras, then we stitch and upsample the camera out of the output out of each camera, and this results into a 3D point cloud. So as it is actually as complicated as it sounds. So uh, this could be solved by our approach. So in our approach, we're just simulating directly everything with ray tracing. So firstly, I think ray tracing is pretty popular right now. Like since 2018, almost all of the GPU manufacturers are including ray tracing in their GPUs, special dedicated hardware for that. So it's very popular currently. But still, let's talk about what is ray tracing. So basically, ray tracing is a rendering technique that simulates the physical path of light by tracing the path through each pixel in a virtual screen and calculating the object visible through it. So it is like taking a 2D photo, like same as rasterization of a 3D world. You take a 2D image out of it, but what's different here is we trace the individual light beams, light rays, so that we get the clear path out of them. So in this, so for this, the dedicated hardware is seen in almost all the modern GPUs. Like you could talk about Nvidia RTX series, AMD Radeon RTX 6000 series and above, and sorry, RX 6000 series and above, Intel Arc GPUs, even Apple M series GPUs, like, and even the A17 Pro, which is a uh, for mobile phones. So you see that as well, and even in the latest Snapdragon and MediaTek chips dedicated for mobile. So ray tracing is becoming very popular nowadays. So as we move on, this is a simple demonstration. So what is ray tracing? What was ray tracing designed for is photorealism, photorealism in rendering, and basically for games. So as you could see, there's actually a camera or a virtual eye, you could say, there's that we use. So instead of shooting thousands and like almost infinite number of light rays from a light source and then tracing them towards the camera, the process is slightly uh, more clever than that. So it shoots rays from the camera and then traces all the rays that actually hit the light source directly. So this way they can uh, directly see that which ray would hit a shadow region and which ray would hit actually lit up region. So this way, the actual image produced out of it is very realistic and close to what actually there is in nature. So many of the modern games use this, and it is actually pretty good. So how can we use ray tracing for our LiDAR simulation? So obviously, the LiDAR, what ray tracing deals with light rays, and so does the LiDAR. So for every laser in LiDAR's scan pattern, we create a ray, and we create a direction for it according to the step size and all the angles and the pose of the sensor and everything. And then creating all the 3D directions, we pass it on to the GPU. The GPU takes over, and because it has the dedicated hardware accelerated ray tracing, so it just calculates the intersection point of the ray with the first object. Because in LiDAR, I don't think we reflections matter. So the first interaction that we see, that point is taken from the scene geometry, and then all these interaction points together, they build a 3D cloud, 3D point cloud. So you could see that this is a very simple process and a rather direct simulation as compared to rasterization. So the 3D scene can be directly converted into a 3D point cloud using all the intersection points from the rays. Um, why exactly is ray tracing a better approach? Because of physically accurate, because how LiDAR works, it is directly simulated in ray tracing. Then no stitching, obviously, because you're directly rendering the light points and the intersection points for it. No stitching like rasterization process and multiple camera is needed. And when we talk about performance, obviously, ray tracing is also rather heavy, expensive process on your GPU, but the scope of LiDAR is like too small for the modern GPUs, so they're very capable of running it. So, like I have a Nvidia RTX GPU, and it runs very good on that. So it is all like, if we talk about a single ray, it is obviously slower than rasterization, but all the stitching and the multiple camera thing that the Gazebo brings in to simulate LiDAR. So in overall, the process is quite fast for LiDAR. So we're just using as you saw, using a LiDAR is like pretty like so much better for the ray tracing. Sorry. So just moving on. So now that we have decided to use ray tracing for LiDAR simulations, how do we actually implement it? So let's talk about the AI landscape, the GPU APIs that we can use to simulate LiDAR. So let's first talk about proprietary APIs. So these would include APIs like CUDA and optics from Nvidia. So these actually give us the best possible uh, performance on Nvidia hardware, but they are strictly vendor locked. So that is why it is not suitable for our project, because we want something that is not vendor locked, and it's runs on all the modern GPUs that actually have ray tracing support. For that, if we dive deeper and go into low level graphics APIs like Vulkan and DirectX 12 and Metal. So Vulkan is a graphics API that is like the newer version of optics, and also it is available on multiple vendors, but it is the very complex and verbose. So using Vulkan for this project is not optimal. And DirectX 12 is only available on Windows, and Metal is exclusive to Apple. So if all these complexities exist, what is the solution for them? The solution would be modern abstraction APIs like WebGPU and its Rust implementation WGPU. So basically what WGPU is a Rust crate. Um, that is a abstraction of multiple APIs that GPU APIs like Vulkan and Metal and Optics. So like uh, if you could see, if it integrates DirectX 12, Vulkan, and Metal, so theoretically it should run on every platform there is for GPU computing. So this is truly cross platform. It works on Vulkan, Metal, DirectX. So obviously it is cross platform, and because it is implemented in Rust, it is modern as well as safe, and it is much simpler than Vulkan. So that is why we have chosen to go ahead with WGPU here. So it gives us best of all the worlds, and we get the latest performance of all the API as well as true platform portability as required. So if we're gonna use WGPU, obviously we're gonna use Rust. So this brings in a new problem: integration. So integration between the the vast C++ world of Gazebo and the Rust side of WGPU. So the core challenges for this would be obviously that the entire Gazebo is built in C++ and it uses CMake and Colcon, but the ray tracing engine WGPU that we're using is entirely in Rust and uses Cargo for the build. So making them work together is quite a complicated process. So like if you could see here, Gazebo world uses C++, CMake, and entity component system, as well as the ray tracing engine. WGPU uses Rust and Cargo. So for this, bridge needs to be made. So this consists of a FFI, foreign function implementation interface, sorry, corrosion, and memory management, because Rust is memory safe, but manual memory management is required in C++. So obviously there would be some memory management issues here. And futures like Gazebo is entirely a synced process, but GPU computing, when you talk about WGPU, it's mostly an async process. So we would need to focus on that as well. So challenge number one, obviously the language barrier: C++, Rust, C++. So how do they communicate? So we have implemented a foreign function interface, an FFI, where we have created a C compatible API in Rust and a corresponding C++ header. So the C compatible API would be lib.rs that you could find in Rust system, and the uh, header file would be rustbinding.h. So for example, if I've taken a function here that just adds the vertices to the mesh. So as you could see that we have used the hashtag no mangle pub extension. So this is what makes the API C compatible. And this is the header file that interacts with the Rust side as well as the C++ side. So the extern C is what makes it available on both the sides. So this is a implementation of FFI. Moving on, the build system barrier. Obviously, as we talked about, Gazebo uses Colcon and CMake, whereas the Rust side uses Cargo. So how do you? So if we're making a plugin for Gazebo, obviously it is in C++ and it compiles. It is made through Colcon and CMake. So how exactly would you compile the Rust side? So for this, we have used Corrosion. Corrosion is a CMake extension, which allows us to just import a cargo crate and target it and build it just like any other C++ library. So this is the snippet from the CMake lists that shows that how corrosion is implemented here. Moving on, memory management. As I told you earlier, that obviously Rust is memory safe, and so it cleans the memory that does not have a owner and is no longer in use. And the C++, all the memory management is done manually. So therefore, there would be obviously some clashes and memory leaks. So how do we fix that? So we've carefully implemented a C compatible struct on the rustbinding.h, and this holds all the important data like the point cloud, the outputs that we get, the image data, the point cloud data, all are stored here. Even the mesh is created here so that the rest does not delete it out of no owner or something like that. So, and we have to be very careful about who owns the set of current memory so that the freeing part of it is good. So as you could see, a mesh struct is created here, and another. So this is just a create mesh function, and this is a free mesh function. So the free mesh function you could see here. So this is exactly where the the memory is freed, but this is called in the inside the main plugin file, the WGPU sensor.cc is this is the main plugin file. So in post update, when after we have built the scene, we no longer need the mesh in the memory. So we're not letting Rust clear the memory on it by itself, but we're manually doing it when we're done with it on the C++ side. So this has been implemented in almost all type of structs, even the outputs, and so this is just an example of that. And the last part, the last challenge would be the execution barrier, sync versus async. So Gazebo is update loop is synchronous and it runs step by step, whereas GPU processing, especially using WGPU, is mostly asynchronous. So what is asynchronous is you give a command and you wait till it gets completed and then you continue the process again. So that is why for this we have to stop the process on Gazebo's side as well, so that till we get an output from our rendering engine, the process is not does not go ahead synchronously. So for this, we have used the Rust library called futures, and this is where we block and just wait for the GPU operations to finish. This is implemented here, where you could see that futures executed block on. So this is for the render depth camera function. So till this finishes and we actually get a depth cam, the output of it, the whole process is blocked. And I've also included how the image data struct is used here to store the output from it. And then this struct is, there is a free function for this struct, and this is actually freed when we're done with it on the Rust side after the transport is complete. So let's talk about the current project status. So where we are right now. So as I've told you earlier, we're roughly at the midpoint of my Google Summer of Code term, and all the foundational work is complete. Like we're you could say that we're almost at the alpha stage where the most of the basic tasks run. We are able to render a depth camera, we're able to render a LiDAR, and the performance outputs are pretty good. So we're all the foundational work is complete, and now we're just try to polish things further and expand more. So the core ray tracing engine is working. We have the Gazebo integration working, and the multi-sensor support is also tested. And I've included that in the demo. So we're able to run multiple distinct sensors as well simultaneously on the GPU. And we can see a real-time visualization either on the Gazebo image display for the depth camera or rerun for the uh, LiDAR output. Also, the engine can render scenes composed of meshes, boxes, and planes. So mostly all type of scene geometries are supported. We're planning on expanding that further as well. So let's talk about the demo that I have prepared. So firstly, it's a scene. So let me just give you a brief description about it. So there's a few objects there: a ground plane, a large wall, a static red car, and a blue car. And the sensors, as I've told you earlier, we have used multiple sensors. So a 360-degree 16 beam LiDAR and a helicopter view of 256 by 256 depth camera. Sorry, I just skipped through. And so how do we actually integrate these in our SDF? So firstly, we include the world plugin, the custom plugin that we have created. And this is how you actually include the plugin. This is a world plugin. So you just add it to your world like all the other plugins. Then we include the custom sensor, uh, like we create a plane or cube wherever we need a sensor, and then we create a custom sensor as we have developed on our side. So there's sensor name, then type is custom, and then there's two GZ types, RT camera, and as you could see here, RT LiDAR. So then the standard SDF parameters like always on, update rate, topic. The topic is actually the topic that is published to, and then the standard camera parameters like the image width and height. So we're taking 256 by 256 pixels here. Then the horizontal FOV and the near and the far clip. So some of these parameters are actually not implemented yet completely. and we're working on it right now. So this is a basic custom GZ RT camera implementation. Moving on, custom sensor for LiDAR. So it is like here also we have tried to follow the standard LiDAR parameters from an SDF example. So there's in this inside the scan, there's the number of lasers, then the steps 360 that we need, then for vertical minimum angle, maximum angle, and the step size is calculated out of these angles. Then from the horizontal, the same minimum and maximum angles, and then the step size is calculated from that. So here the horizontal angle would be like from -180 to +180 degrees. So that's a complete 360 degree. And we're using 16 lasers here. Then we're using minimum and maximum range. And so as you could see that noise has not been included yet. So we're going to do that soon. This is a demo. So this is a video that I've prepared. So you launch the example. You could see there's the wall, there's a ground plane and two cars. So this cube that you could see here, this is the LiDAR, and I'm not sure that we could see, but there's somewhere on the top is the helicopter view of our depth camera as well. So the depth camera publishes the data to GZ topic that we included in our SDF file, and so does the LiDAR, but we're having trouble visualizing it using ROS bridge and RViz right now. So we've just included rerun for that right now. So as you could see, we just open up the image display in Gazebo. It automatically subscribed to the image output. And this is the rerun visualization that we see. And it is using 16 lasers. The LiDAR is using 16 lasers. And we get a 360 view of the output. So, and this is the depth camera output. This cube that you see, it's the LiDAR, and you see this car and that car. So it actually is a bit cropped because of the FOV and the pixels, but yeah, you could see that this is pretty accurate. And same goes for the LiDAR. And this is a image, the screenshot that I've included to just display the render timings. You could see that the render timings here are pretty low. So for a 16 lasers LiDAR, that is a 360-degree view with 360 step size, its render time is 9.26 milliseconds. And for the depth camera, it's 4.71 milliseconds. So using the current method, I suppose for this particular example, the render time for the LiDAR using rasterization would be somewhere around 50 to 60 milliseconds. So you could say that we're at least 5 times faster. So this approach is at least 5 times faster. And so this you could have a good look at the LiDAR output here. This is the blue hatchback car that we see. You could see that this is pretty accurate, and you could see the shape of the car. The wheels are here, the mirror is here. Same goes for the car on the side and the wall as well. So as you could see, this is a pretty accurate output, and it is fast as well. So what would be the future work? So firstly, obviously the performance and optimization. So we would try multi-threading. Like if, I told you earlier, the rendering is an async process. So if we create a thread out of it, so that could enhance things. And we will just try for multi-threading to improve performance as of now. And then we have to benchmark. So like all these results that we see right now, these are not properly benchmarked yet. So a properly intended benchmarking process. Then for this particular example, the best results were LiDAR output less than 10 milliseconds, as we just saw here, and the depth camera output less than 5 milliseconds. So the performance wise, we're doing pretty great for a single thread for just an alpha version and single thread. And I think as we deploy more optimization techniques, we might get better results as well. Then after that, the next goal would be ROS2 and Gazebo integration. We can send the data over Gazebo GZ topic as of now, but visualizing the LiDAR data on RViz using the standard ROS2 workflow, creating a ROS2 launch file and all that, that is still left. And maybe in the distant future, creating the package out of this whole plugin so that it could be installed directly as a ROS2 package and just ready to use inside Gazebo. Then expanding capabilities. So we have just implemented a plane, a box, and meshes as of yet, and that includes like all the scenes that you might want to create, but just simple SDF geometries like cylinders and spheres that are commonly used. Uh, it's an easy process, so this is not a complicated task. We can get it done with in a few hours and only. So expanding the SDF support, and then using advanced sensor features, like as I told you earlier, we're not using noise yet, and we are not using intensity returns as well, so we could use that in the future and implement some more parameters that might be useful. And new sensor types, this is a fairly complex goal, and including new sensor types like sonar or even radio frequency or wireless communication, that's fairly complex, but that is something that is possible and we can target later on. So that is it. So this is the, you can find the repository here, and any feedback and contributions are welcome. Please visit the repository. Here's a QR code. If anyone wants, just they can take a screenshot or they can scan it right now. Should I wait or just move on to the next slide?
Yeah, whatever you prefer.
Yeah, so that is it. Thank you. And any sort of questions are welcome. And special thanks to my GSoC mentor Arjo and the entire Open Robotics team. It has been a very good experience till now, and let's hope I can get some good work done in the future as well. You can find me on GitHub. This is my GitHub link, and this is my email. You can find me here. So thanks.
Well, thanks to you, of course. So round of applause for you, Shashank and Arjo. This looks very promising. I agree. Like very nice exploration and very good results so far. There's a question here from Usama on the chat. What is the timeline for the project, and when do you expect this to be integrated into Gazebo?
The official GSoC timeline is from like June to September, and I'm more than halfway through it. So we're done with it. And as of Gazebo integration, I think Arjo should answer that.
Arjo.
Yeah, so as you can see, this is a bit of an interesting project because it's mixing Rust and C++ in very interesting ways. So I think the actual Gazebo integration will be a conversation that's going to take some time to discuss and actually figure out how best to, package things in a way that everyone's happy and reliable and satisfies the IP dependencies and whatever else requirements we have. So yeah, I think that's an unknown, but yeah.
More questions for Shashank and Arjo.
Yeah, if you build from source, you can use it today. It's buggy.
Yeah, it has some bugs, and some of things are still in under not merged yet. They're still as a pull request, but I think we'll be able to create a very good alpha version type of thing soon.
Question about the performance introducing the bridge between C++ and Rust.
I think this is a very good topic to talk about, but as I've told you earlier, like I've just finished the actual LiDAR implementation just last week, and it was still buggy till today, and I just finished a lot of things today. So the actual marking for all this is still left, but I don't think there would be much of a performance hit, something around 20 to 30% we're talking. So let's see. I'll be available. I think I'll have pretty good benchmarking results soon about that. And as soon as I have it, this would be updated on the README in the GitHub. So yeah, do check that out.
Jose?
Yeah, this is an amazing project. I think it's mixing one of the most trendy things in the moment, that is Rust. I think something like a simulator can probably benefit quite a lot from running getting the Rust performance. So exciting! It's the first time I see like Rust integrated into the project. Not only collaborating with it via GCP transport, but it's fully integrated even in CMake. So congrats. That's probably one side. So question: have you guys checked what's the difference in time about running this LiDAR implementation against the current existing one in Gazebo?
Yeah, so you could see the results we're getting here for the LiDAR, 16 lasers LiDAR of a 360-degree view. It's somewhere a little bit less than 10 milliseconds. And we did, I did not check it officially, but as far as I've tested with some other examples, I think this might take somewhere around 40 to 50 milliseconds on the current rendering of LiDAR. So we're talking about a 4 or 5x gain on performance here. And this is pre-optimization. So as we try and do more optimization of stuff, we might get better results.
Yep. Thanks.
Addition?
Yeah, great project, as everybody said. Really impressive work. I was looking at the video you had and saw that the RTF was still pretty low, which made me think, are you doing, and you said this is a sync process, right? Sync, the current sensor system, the way it works is it launches off a thread and does the rendering in the background, immediately returns so that Gazebo continues to do the other simulation things, and then only tries to re-render when it's necessary for the next frame. So like if the sensor is a 15 hertz sensor, it doesn't try to render every single time step, right? So are we taking that into account in this, or is that not yet done?
Actually, the update rate, it has not been fully implemented yet. So I think that is a issue here. And also the real-time factor, I think we're taking the physics of 1 millisecond here. And as you could see that the rendering time takes 5 milliseconds and 10 milliseconds respectively for the depth camera and LiDAR, and include some Gazebo overhead, the C++ overhead for that. And that is why we're getting such low RTF, because of we're taking 1 milliseconds. But in a example, I don't think anyone would actually take 1 milliseconds. But I think after we actually include the update rate and update the scene according to the update rate, I think we're gonna get better results about that.
So yeah, I'd like to point out that this is like midway through the GSoC, so we haven't yet got to the point where we are putting in a separate thread. We're just keeping it simple to show that it works.
Cool. Yeah, I just wondered. That sounds good that you know about it and you're planning to take care of it. So the other thing I was wondering was it not possible to visualize the LiDAR image, the LiDAR sensor data inside Gazebo? There's like a LiDAR visualization plugin in the GUI. Did that not work for some reason?
Yeah, there is a point cloud visualizer, but that was not working. Like I saw on the subscribing to the topic just on the terminal, and we were getting an output, but for some reason the Gazebo was not working as expected. So hence we just used Readin. And I think as far as I know, this is like the point cloud visualizer for LiDAR is like not very good on the Gazebo side. Like there is float vector issue or something like that. I think Arjo might be able to answer about that.
So I think I think it's just it's tricky to so for the purpose of our development process, we often rely on rerun internally because that allows us to debug like the ground state of the system. And so You can take out rerun and disable it, but we rely heavily on it internally for that kind of debugging work. But the point being that I think there was I just told Shashank to keep it as simple as possible, and we were having some difficulty doing that rendering, and so that's very much next on the bucket. And if we figure out what the bug is, that'll be a PR to fix it.
Maybe you have time for one more question, Ian.
Thanks. This is awesome work. My first question was actually related to Aditsu's, but I think you're aware of the RTF issue. If you're updating at 10 hertz and then the LiDAR takes 9 milliseconds, I think you can. There's some improvement that to get the real time factor up quite a bit. Like what Gazebo is currently doing now is that the physics engine can continue stepping and then rendering will render. So if it's doing update rate at 10 hertz and it takes 9 milliseconds, we should be able to bump up the RTF quite a bit back up there. The other question is, like with Ogre 2, there's a bit of a memory issue when creating camera and lots of render textures to do LiDAR. That's one big issue. I don't know if you have time to just look at the memory consumption there in your use case. I imagine it's probably going to be much better, but I just was curious to know if you've done any analysis there.
I think we haven't done any analysis on the memory side yet, but looking at just the way things work, you load the scene once into the world. So the way ray tracing works on the hardware is like you generate like this bounding volume hierarchy. So it's like you have kind of like, if you're in robotics, Octomap, like it's a hardware implementation of that kind of binary space, the dividing tree, right? So you just load the scene once, and then after that, you just once it's in memory, you don't need to do any touching. And then like the back and forth, there's no need to allocate separate textures. It's just one texture for the point cloud.
Okay, cool. It'd be awesome to see some numbers.
All right. I think it's about time. So I'd like to thank everybody, and especially our guests today for joining and also for presenting this project. We'll definitely keep looking into it to see how it progresses and how can we integrate it, because it looks promising. Have a good one, everybody. And as we said, we'll see you next month for the tutorial party. Have a good one.